Assalamualaikum everyone. Today I will be presenting our research titled A Dual Path Hybrid Convolutional Neural Network and Bidirectional Long Short-Term Memory Approach for PPG-Based Research Monitoring. This work has been accepted to the 4th Muslims in Machine Learning workshop co-located with ICML 2025. This work is a collaborative effort between Russia University of Engineering and Technology and King Fahd University of Petroleum and Minerals. I am Mohammod and I will guide you through the motivation, architecture and results of our proposed model for real-time stress detection using PPG signals. Objectives. Let us begin by outlining the motivation and key objectives behind this work. Mental stress is a growing public health issue. It can lead to serious physiological and psychological consequences, such as hypertension, hormonal imbalances, anxiety, and depression. Therefore, effective stress monitoring is critical for early intervention and mental well-being. Our aim was to develop a method that allows continuous non-invasive and real-time stress detection, and that's where PPG comes in. PPG or Photoplethysmography is a light-based method that measures changes in volume in microvascular changes in blood volume in the microvascular bed tissue. It is low-cost, widely available in wearable devices, and sensitive to stress-induced physiological changes. Now, materials and method. Moving on to the dataset used in this study, we used WESAD dataset, which stands for Wearable Stress and Effect Detection. It is a publicly available multimodal dataset widely used for stress detection research. The dataset contains PPG signals sampled at 64 Hz, collected from 15 subjects. Let us dive into signal preprocessing. Before feeding the data into our model, we applied a few essential preprocessing steps. First, we divided the continuous PPG signals into 30-second non-overlapping segments to form consistent input samples. Then we applied Z-score normalization to each segment, standardizing them to zero mean and unit variance. We also applied sliding window-based augmentation approach to train data for balance the classes. Now let's look at the architecture of our proposed deep learning model. We designed a dual path architecture to extract both spatial and temporal features from the raw PPG signal. The first path uses a combination of CNN, Bi-LSTM and LSTM layers to capture hierarchical and sequential patterns in the signal. The second path is a lightweight CNN-only branch which runs in parallel to provide faster complementary feature extraction. These two paths are then concatenated and passed through a final classification block. Despite its strong performance, the model has only 1.38 million parameters, making it highly suitable for real-time resource-constrained environment like smartwatches or fitness bands. Results. Let us now look at how well our model performed. We evaluated our model using leave one subject out cross-validation both with and without data augmentation. Without augmentation, the model achieved 95.9% accuracy. On the other hand, with augmentation strategy applied, the performance further improved to 97.9%, along with improvements in other metrics. This clearly demonstrates not only the strength of the model but also the impact of augmentation in handling class imbalance. Let us dive into the comparison with state-of-the-art architecture. To benchmark our model's performance, we compared it against several state-of-the-art models. As shown in the table 2, our model outperformed all them across most metrics, particularly in terms of accuracy, specificity, sensitivity, and AUC. This validates the effectiveness of our architecture in processing raw PPG signals for stress detection. Interpretability. To further validate our model, we examined how well it learned to separate emotional states. We visualized extracted features using TSNE, a dimensionality reduction technique that helps reveal clusters in high-dimensional data. As the figure 3 shows, feature separability becomes more pronounced in deeper layers. This gives us confidence in the interpretability and robustness of the learned features. Conclusions. To summarize, we proposed a lightweight and dual-path deep learning model for PPG-based stress detection. The model operates directly on raw signals, eliminating the need for manual feature engineering. It achieved a 97.9% accuracy and outperformed multiple state-of-the-art models with only 1.38 million parameters. It is ideal for wearable deployment. In future work, we plan to expand our model to multi-class emotional classification and explore real-time deployment on edge devices for use in everyday environments. If you have any question or are interested in collaboration, please feel free to contact me using the email provided here. Thank you so much for your time and attention.